Alright, so here we go. We're going to put a little Christmas bow on our talk with our discussion here on binomial distributions. So looking at this note sheet, what we wanted to look at now is looking at the shape of a binomial distribution. So what we're looking at right down here is we see 5 distribution charts, and with each one of these, the number of people that we were randomly selecting kept on going up. So once you're looking at these here, you can see that we go here, we look at 5 people, and then we go to 10, and then it goes to 25, and then we look at what if we sampled 50 people, and then what if we sampled 100 people. So what this study was doing here is, suppose if we were looking at 5 people randomly selected, the population in the U.S., the number of children were counted, and I guess they're defining children as 13 years or younger. And what they were doing is when they looked at, say, for example, 5 people were polled, they counted the number of children in that group. And when you're looking at this chart here, one thing I'd like you to notice is this first bar graph. There's 0 children. They said, well, in their study here, they noticed that about around a little bit over 30%. Here in the study, once they conducted a 5-person study, about 30% of the studies showed that you didn't get any children in the group. And that's kind of what this passage is looking at right here, if we take a step back and take a look at that. It kind of says that right here, doesn't it? So in just over 30%, the 5-person samples, there were no children present. In 40% of the 5-person samples, only 1 child was present. So you can see in this chart right down here, 40% of those studies, you can see with the second bar right there, that's one child. So if you look here at these bars, notice you have 5 bars here for 0, and then 1, 2, and 3, and then you see something right down there with a very, very small percentage of giving all 5 of them. And so notice what happens here as we keep on looking at larger and larger sample sizes is that the data gets more and more and more looking like this guy right down here. So does this look familiar? Yeah, this is our bell curve that we've been dealing with here. And what this bell curve is kind of showing is that the number of children, once they took a sample size of 100, they noticed that about a big percentage of it, so a little bit under 100%, a little bit under 10% right there, the biggest chunk of it, we end up running across 20 children in that set of 100. So as you can see with all these distributions, not all of them were normal. You can look at these ones right. This one right here definitely was not a normal distribution. But as we kept on increasing, it got more and more like that normal distribution that we know and love. And this phenomena is triggered because from the fact that we keep on doing larger and larger and larger sample sizes. So with large sample sizes, the distribution looks more like a normal distribution. So with a large enough sample size, the closer it gets to be a normal distribution. And what we call this right down here, and you put this on your note page, this is called the rule of 10. And what the rule of 10 states is that the shape of binomial distribution will be approximately normal if the expected number of successes is 10 or more and the expected number of failures is 10 or more. Okay? So we can write this here as just a series of formulas, just basically like this. Remember, yesterday we talked about how to calculate the expected number. We take that probability of success and we multiply it by the number of trials. And if we have the number of successes as 10 or more, then we can say that that distribution will be approximately normal. So what we're going to write here is 10 or more. Well, that would be thought of as like this. P times N needs to be greater than or equal to 10. Hey, that kind of rhymes. But also, don't forget here, for a distribution to be approximately normal, the number of failures, the expected number of failures needs to be 10 or more. So I think if I remember right, we define that as 1 minus the probability of success. Remember, the probability here is always expressed as a decimal. So that's why we're using 1 to represent 100%. Multiply that times n. That also needs to be greater than or equal to 10. So in the next video here, we're going to practice a little bit.